All right, where we left off is we said we were going to start talking about reactions of these benzene derivatives. Okay? And what we first did is reminded ourselves that when we talked about alkenes, alkenes undergo addition reactions, right? So we're breaking that pi bond and we're adding a new single bond on either side. All right? Our benzene derivatives, though, they do not undergo addition reactions, right? In order for benzene to undergo an addition reaction, it would also have to break one of those pi bonds and replace it with two new single bonds. And it doesn't want to do that because then it goes from being an aromatic compound to a non-aromatic. And remember, aromatic, nice and stable and good. So it's not going to break that aromaticity in order to form these new bonds. And so instead what we said is that these benzene derivatives are going to undergo what are called substitution reactions. We're going to replace one of the hydrogens around that ring, right? And just to be clear, when we look at benzene, we need to make sure that we fill in with our mind's eye here. Whoa, not that. All of those implied hydrogens, all 6 of those implied hydrogens around the ring here, right? So in our substitution reactions, we're going to take one of those hydrogens and substitute it or replace it for another bond, all right? And in that way, we still get our aromatic product, right? We start out with an aromatic ring, we end with an aromatic ring, okay? So again, unlike alkenes, we're going to see that these benzene derivatives do not undergo addition reactions, but rather substitution reactions. All right, and this is a particular class of reactions called electrophilic, aromatic substitution. All right, also referred to as simply EAS for short. All right, so by the end of the day, we'll have introduced a few reactions that fall under this category here. But first thing we need to do is to introduce some terminology, which is particularly important in organic chemistry. We see this first word, electrophilic. All right, so all organic reactions, all reactions in organic chemistry are follow this basic scheme where you have something with a lot of electrons that's reacting with something that's relatively electron deficient, and that's why that reaction occurs. So we have these fancy terms. We have what's called the electrophile. Let's try to pick this word apart here. What does that suffix phile mean? Does anybody know? Lover, exactly, right? So this would be an electron lover here, an electrophile. So this is something that really wants electrons because it itself is electron poor. Okay? So our electrophile in our reactions is an electron lover. Because it is electron deficient. All right. Our other species in our chemical reaction we call the nucleophile. Again, that same suffix phile. So these are nucleus lovers, or species that really want to react with that positively charged nucleus. And they're attracted to that positively charged nucleus because they are electron rich. right? And so this is what is important to keep in mind here. We have our electrophiles, which are electron deficient, and we have our nucleophiles, which are electron rich. And what we say in our chemical reactions are that nucleophiles attack electrophiles to form new bonds in a chemical reaction. Right? So our organic reactions, they follow this scheme where you have this electron-rich molecule attacking this electron-poor molecule, forming these new covalent bonds. Okay? This is kind of the basic scheme. All organic reactions kind of follow this principle here. You have something that has a lot of electrons, it's going to react with something that doesn't have a lot of electrons. All right? In our electrophilic aromatic substitution reactions, so now we're specifically talking about these aromatic benzene derivatives. All right, and in these reactions, the benzene ring is the one that plays the role of the nucleophile. Right? It is the electron-rich species in these reactions, and in particular, we're talking about those pi bonds. Right? Those pi bond electrons are that electron-rich part of that molecule. All right, we didn't really introduce this terminology previously, but we would have seen the same thing with alkenes as well. Alkenes, that pi bond is that electron-rich species in those addition reactions. All right, so now we're just kind of introducing some fancy terminology, which is pretty universal throughout organic chemistry, our nucleophile. And in these reactions, it's going to react with some electrophile. I'm just going to use this generic E, and I'm going to give it a positive charge to remind us that our electrophiles are electron-poor species. All right, so our nucleophiles are going to react with some electrophile. And we're going to get our EAS reaction, our electrophilic aromatic substitution reaction. Where one of those hydrogens on that benzene ring gets replaced by that electrophile. All right, and what we're going to show is that we could use a few different electrophiles and thus get a bit different product in our electrophilic aromatic substitution reaction. All right, we're going to learn a few different types of these electrophilic aromatic substitution reactions, but importantly, what we're just learned is that benzene is our nucleophile in these reactions, is our electron-rich species, and it's those pi bonds in that benzene ring that make it electron-rich, right? We got all those electrons floating around that ring. All right, so we're going to look at a few specific ones here. First is what's called a halogenation reaction. All right, we got our benzene ring. All right, and we kind of teased this last time, but benzene will also react with our halogens. So for example, bromine. All right, but instead of having those addition reactions, we just get our substitution reaction. All right, and even though we can leave our hydrogens implied, I want to make a point here. So I'm going to draw in this hydrogen on my benzene so that I can show that it gets replaced or substituted by a bromine on that ring. All right, so two things to note here. Bromine is a diatomic element like our other halogens. So when you find bromine out there in the wild, it's not individual bromine atoms floating around, but Br2 molecules, right? Bromine's diatomic, always found in pairs. When we do our substitution reaction, I am not putting both bromines on that ring. There is only one of those bromine atoms that end up on that ring. If we were worried about, well, what happens to the other one? If we were drawing our balanced chemical equation here, we would see that we have a hydrogen and a bromine on the reactant side that are unaccounted for, and we get this extra product HBr. All right, that's my balanced chemical equation, but again, in organic chemistry, we always get lazy. We don't really care about our inorganic products. Right? HBr is not our organic product, but our inorganic product, and we omit those in our chemical equations. So you look at this and you're like, hey, where did that bromine go? It's there, it's accounted for, all right, but it's just not what we care about because it's not going to be incorporated into our hydrocarbon at all, right? So again, only one of those bromines is going to react and attach itself on the ring. What I think a lot of people are going to be tempted to do, which is wrong, is to say Br2 on that ring. This is not correct. All right, you can't even have your octet rules satisfied that way. Cool. All right, the other thing is we said that benzene plays the role of the nucleophile in these reactions. Well, in the grand scheme of things, benzene isn't really a fantastic nucleophile. It's kind of meh. All right, so in order to get these reactions to occur on any sort of a time scale that's not going to take a million years, we always use a catalyst in these electrophilic aromatic substitution reactions. So it's not just bromine you're going to see in your reaction arrow, but also the catalyst, either iron or aluminum bromide. Either one of these would work. AlBr3. All right, so we have our substrate, that organic molecule, our benzene. We're treating that with our reagent, that inorganic bromine. That's what's being consumed in this reaction. And then we have a catalyst, which is either iron or aluminum bromide. Catalysts don't get consumed in the reaction, so they're kind of kept in a different category than our reagents. But nonetheless, they're necessary for the reaction to occur on any sort of a reasonable time scale. I.e., I want this done in the next hour, not the next 3 months. All right, cool. So we can use bromine. All right, another halogen that works would be chlorine. Chlorine is, again, diatomic. And we, again, need a catalyst. All right, we can use either iron or aluminum chloride. And everybody take a second, based on analogy of what we did before, give me the organic product of this reaction here. right, so again, what we're going to do is we're going to substitute that hydrogen for that halogen. In this case, my halogen is chlorine. And again, only one of those Cl2s makes it on the ring. The other one is off as an inorganic product in our solution. All right, so, and these are the only two halogens that really work for this, bromine and chlorine. All right, we can do these halogenation reactions using either bromine and chlorine, and then again, we always need a catalyst. I sort of mix it up with both. You'll see either iron or aluminum bromide as your catalyst, or if we're using chlorine, aluminum chloride. All right, so that's how we can stick a halogen on our ring. All right, the next class is what are called nitration, or I guess it's only one reaction. The next reaction is what's called a nitration reaction. All right, here we're going to substitute H for a nitro group, which has that formula NO2. All right, again, starting out with our benzene ring here. In order to do these nitration reactions, you use nitric acid, HNO3. All right, but you also need, that's your reagent, but you also need a catalyst. So you dump in an even stronger acid, sulfuric acid, to help catalyze this reaction. All right, and this will replace that hydrogen with a nitro group, NO2. All right, so just note that we go from having nitric acid, which is HNO3, and we only have in our product NO2, that nitro group. All right, so again, we have an inorganic product here that's lost in this reaction. Turns out that water is also a byproduct of this reaction, but again, we get lazy and we don't care about the inorganic. All right, so just note, even though you're starting out with nitric acid, which is that formula HNO3, you're only adding NO2 onto that ring. All right, one other thing to note about our nitro group here, because this is our condensed way of writing, which is really convenient, but when it's our homework, we have to draw out the full Lewis structure of these nitro groups. All right, so that is nitrogen double bonded to one oxygen and then single bonded to the other. All right, everybody take a minute and fill in lone pairs and formal charges on this molecule. Nitrogen with its 4 bonds should have a positive formal charge. Oxygen, if it's got 2 bonds, it should have 2 lone pairs and no formal charge. And my other oxygen with just 1 bond should have 3 lone pairs and a formal charge of -1. Okay? Those lone pairs and those formal charges are important for the structure of this molecule, so make sure to include those. All right, so We can put a nitro group on this ring, substitute out one of those hydrogens for a nitro group by using our reagent nitric acid, and then our catalyst sulfuric acid is important to drive this reaction. Okay. Now we got a sulfonation reaction. Here we're going to substitute our hydrogen in our ring for what's called a sulfonic acid group, SO3H. So here we're also going to use sulfuric acid, all right? But it turns out that just sulfuric acid by itself isn't enough to drive this reaction. You got to use what's called fuming sulfuric acid. Basically just heated up and boiled, and it's reacting with the gases in the fumes above that mixture. All right, this will take our ring, and I guess I'll draw in this hydrogen that we're going to replace. With a sulfonic acid group. SO3H. Okay, so again, we have another one of these substitution reactions. We're just putting a different electrophile on that ring here. All right. Again, our homework is going to have us draw out the full structure of this here. And this one's a little weird because let's just look at it real quick. SO3H. And what looks so weird about this functional group here is we look at our sulfur and we're like, hey, what the heck? How many bonds does that thing have? We have a total 1, 2, 3, 4, 5, 6. So there are 12 electrons in sulfur's octet here, and that's okay. All right, so what we would have learned back in like Chem 1A when we were talking about our Lewis structures. Ignore all that, that's not y'all. Is that our larger elements starting in row 3 and below can have what's called an expanded octet. And that was part of why you had this big pain in the butt procedure of calculating valence electrons and going through and blah, 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 blah. When we got to organic chemistry, we said, oh, we can simplify our rules down, right? Carbon likes 4 bonds, nitrogen likes 3 in a lone pair. And we were able to get away with it because we were focused on only these smaller elements up at the top here, right? So sulfur follows some different rules than our normal organic chemistry elements. Sulfur can have an expanded octet, all right? You're just gonna trust me that this is what that group looks like.
Does it have like a specific charge because it has
It actually doesn't have a formal charge here because it's still, if you did your formal charge rules, like you learned, it has 1, 2, 3, 4, 5, 6 electrons, and it had 6 valence electrons. So it's actually very happy and stable here. It's just odd. It's a larger element. It can fit more electrons in its octet.
+2 charge, a formal charge?
No, because again, if you like sort of did the formal charge calculation that you had learned, it's number of electrons minus their number of valence electrons. Sulfur has 6 valence electrons when it's all by itself, and it has 6 in this compound here, so it's perfectly happy. Yeah, these things, you see it also in sulfate ions, are remarkably stable. They are very, very happy. They have an expanded octet, but again, that's okay. There's nothing bad about that when we get to our larger elements. Importantly, our smaller elements, they just don't have that option available to them. All right, so the last two are what are called, they get a special name. They're called Friedel-Crafts reactions, named after the scientists that established them. All right, and they kind of get a special mention, a special shout out, because here we're going to do something that we've never learned how to do before, which is create new carbon-carbon bonds, something that's kind of hard to do in chemistry. We're going to be substituting our hydrogen for a new carbon-carbon bond. All right, and there are two different types of Friedel-Crafts reactions, very, very similar. The first one is called a Friedel-Crafts alkylation reaction. So we're going to substitute H for an alkyl group. All right, some amount of carbons and some amount of hydrogens. All right, I'm going to use a very simple alkyl group here, just one carbon. All right, but importantly, our reagent here is an alkyl chloride. All right, and actually, I want to draw the full structure of that CH3Cl. Okay, what we're going to see is this carbon-chlorine bond right here gets replaced with my new carbon-benzene bond. All right, so my product of this reaction here would have that CH3 . All right, I'm going to lose that chlorine in our reaction. And of course, it doesn't vanish into thin air. I just simply mean it's incorporated as one of our inorganic products. All right, these alkylation reactions also require a catalyst, just like all our reactions. And it's actually a familiar catalyst that we've seen before, that aluminum chloride. All right, that aluminum chloride actually pulls that chlorine off of that carbon, making it able to bond to that benzene. All right, so let's just do one more here. I want you all to try to predict these products. We used a very simple alkyl group, just a methyl chloride. All right, let's take the same thing, but now we're going to use a bigger alkyl group, 2-chlorobutane. All right, so I'm going to start by drawing my product here, my benzene ring. All right, and how many carbons do I need to add to that benzene ring? 4. All right, so counting carbons is particularly important in reactions where you create new carbon-carbon bonds, because the structure that you get at the end is always bigger and uglier than what you started with, right? We're not just swapping out a hydrogen for a chlorine, we're adding a larger portion to this molecule here. So anyway, counting carbons, super important for these reactions where you create new carbon-carbon bonds. I need to add these 1, 2, 3, 4 carbons to my ring, the 4 carbons from my alkyl chloride. All right, so I'm going to draw my new bond. Boom. Okay. What carbon lives on the other side of that bond? Well, importantly, it has to be the one that was attached to the halogen in my reagent here. So I know that this is that big orange carbon, and I'm just going to make sure to fill it out with the remaining bonds there. All right, so that orange carbon had 1 on one side and 2 on the other side. So this is my product here. Again, I can count carbons. I have my 1, 2, 3, 4, 5, 6 for my ring. And I have my 1, 2, 3, 4 from my alkyl chloride. Again, the carbon that had that new carbon-carbon bond formed is the one that was bound to the halogen in my reagent, right? So this big orange carbon here is the one on the other side of my new bond on my product side. All right, we're going to do one more. Make sure we got this down. All right, so I'm going to draw my product. I'm going to start with that benzene ring, and I'm going to draw that new carbon-carbon bond. All right, so what carbon must be on the other side of that new bond? It's got to be the carbon that was bound to my halogen in my reagent here. All right, so that means that's that carbon. I need to include another 1, 2 before I get to my ring. So 1, 2. All right, and now this has this whole friggin' pentagon on here. And because my product is so big and ugly, I'm going to go back and double check by counting carbons to make sure that I have my correct structure here. Very easy double check. All right, cool. I got my 6 from my ring. That was easy enough. Now I should have a total of 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right, so again, count it. It's very easy to draw an extra line or forget to draw a line, right? So going back and counting carbons is the easiest double check that you can do for these reactions. I recommend it always, but especially if you have a reaction that creates a new carbon-carbon bond. Cool. All right, so the other type of Friedel-Crafts reaction is what's called an acylation reaction. This is where we're going to substitute H for what's called an acyl group. All right, and acyl groups just have a carbonyl bond followed by a bunch of carbons and hydrogens. They're the worst named of all the groups. I don't know where acyl came from, but should be like ketone or aldehyde or something similar to that, but I don't know. They're just pulling crap out of their butt. All right, so we're going to attach one of these onto our ring here. Again, starting out with that benzene ring. All right, now we're going to use, okay, we have that acyl group. But importantly, in my reagent, what is attached to that carbonyl carbon is a halogen-like chlorine. And in this reaction, we're going to see the same thing that we did for our Friedel-Crafts alkylation reactions. We have aluminum chloride that's going to remove that chlorine from that reagent and allow us to form a new carbon-carbon bond, this time specifically with that carbonyl carbon. All right, so we're going to draw our new product here. Here's my benzene ring. I'm going to draw my new bond. All right, and again, what lives on the other side of that new bond? What carbon did I form that new bond with? It's the carbon that's attached to that halogen. In this case, it's always going to be a carbonyl carbon. So in this case, I've added these 3 carbons onto my ring here, specifically attaching it at that carbonyl carbon. All right, so let's just put one more example down so we make sure we got this. Cool. All right, so I'm going to draw my benzene ring in my product. When I make my new carbon-carbon bond, the carbon on the other side of that new bond has to be my carbonyl carbon. All right, so I'll put the carbonyl oxygen on there, and I need to make sure to include all 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, all in a row. as well as this one sticking up right here. So again, I'm going to double check. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Cool. All right, so that kind of seems like a lot. We learned 5 of these different electrophilic aromatic substitution reactions. I get 6 if you're going to count those 2 halogenation as 2 different reactions. All right, so let's just make a summary. Of these EAS reactions that we learned here. Okay, so I'm going to make my benzene in the middle of the page here, and then I'm just going to draw, going around in a circle here, all of our different reagents that we introduced here. So we have the bromine and aluminum bromide. Maybe we got 6. Our nitration. All right, there's no real rhyme or reason as to the orientation of these around the ring here. I'm just trying to make enough space to summarize everything. All right, where you're going to take a minute and fill in this ring here, fill out our products. All right, one thing that I'll note is I did for the Friedel-Crafts alkylation and acylation reactions use these R's here. What the heck does that mean? All right, so R is just a stand-in for any number of carbons and hydrogens. So for these alkylation reactions, we saw we can use a bunch of different sized alkyl groups, alkyl halides. So we're going to just leave it as generic R. We can fill in any number of carbons and hydrogens there. All right, but yeah, take a minute and fill out this wheel. This is just a nice little summary of all these different reactions. I feel like when they're spread out across a bunch of different pages, it's a little bit harder to compare and contrast. Here you can see that all we're doing is substituting out that same hydrogen for one of these 6 different things here. right, so we've got these 6 electrophilic aromatic substitution reactions where we're taking benzene and we're removing a hydrogen from that benzene ring to replace it with one of these 6 new groups here. Okay, we can do our alkylation reaction. I again left a generic R group because that just represents like a variable. It represents any amount of carbons and hydrogens on there. We can do our 2 halogenation reactions, put a bromine or a chlorine on the ring. An acylation reaction where we now have a carbonyl carbon attached to our ring, and again, any number of carbons and hydrogens. And then these 2 kind of special groups, what we called a nitro group, we introduced this before, the NO2, as well as that sulfonic acid group SO3H. That's kind of a new one for us. All right, so these are our 6 electrophilic aromatic substitution reactions. I just think that these little wheels are a nice little summary tool for studying, right? Kind of put it all in one place next to each other so we can compare and contrast. Okay? All right, so if I ask you any one of these reactions all by themselves, that's all well and good, right? You can give me the product of that reaction, all right? But the meat of this chapter, the hard part of this chapter is not just looking at these reactions one at a time, but what happens when we start to combine these reactions, okay? So what do I mean by that? Let's take our benzene ring. And I'm going to tell you that we're first going to do that nitration reaction. HNO3 in sulfuric acid. Okay, that's doing just one of these electrophilic aromatic substitution reactions, the one that puts a nitro group on the ring. Also, I guess just to note, I'm always picking this like upper right corner here. That's just completely arbitrary. You could pick any one of these carbons and put that group on there, right? Just rotate the ring and you would get that same structure. Okay, but now let's say I wanted to do a second reaction here, where I'm going to use my bromine and aluminum bromide. All right. I'm going to be substituting a hydrogen on that ring for a bromine, but now we have 3 different possibilities depending on where we put that bromine on the ring. We could put it next door to that nitro group, right? We could put it one removed from that nitro group. Or we could put it on the opposite side of the ring from that nitro group, right? If I do 2 of these reactions in a row, all of a sudden I have these 3 possible products. All right, and we now are going to talk about which is actually formed in this reaction. All right, so you do one electrophilic aromatic substitution reaction, great. You got one product, because you could have picked any carbon and put that group on the ring, same product. But all of a sudden, if I do a second one, now all of a sudden I have 3 distinct products that could form. These are 3 distinct molecules. They have distinct physical properties, right? So we got to ask ourselves which one of these are actually going to be made in our reaction here. Okay? Turns out it's not all of them. All right? It's not just a random sort of distribution of all 3. There's selection here. So first of all, we have special names for these products because of the orientation of these 2 groups around the ring. What do we call them when they're right next to one another? Ortho. So this would be my ortho product. What about when they're one removed? Meta. And when they're on opposite sides of the ring, para. All right, we introduced this terminology before. We're going to use it a lot in this chapter here. Do I get the ortho product, the meta product, the para product, or some combination of more than one? All right, cool. So we're sort of going to just briefly introduce the logic behind this, and then we'll kind of dive deeper into this on next class period. Okay. All right, so it turns out that some of our substituents are what are called electron donating groups. All right, let's remind ourselves that in these reactions, we said benzene is the nucleophile. Are electron-rich species. All right, so now I'm going to take my benzene ring here, and I'm going to put a group on there that's an electron donating group. Like an OH group. I'm going to tell you that this one right here is an electron donating group. And I know that because it's got a lone pair next door to that ring. Right? So this OH group, I can spy it as being an electron donating group because that oxygen atom has a lone pair and is right next to that ring. Okay? All right, so now I'm going to show you what it looks like when that lone pair gets donated to the ring here. All right, and for this course, you're not going to know sort of how I got these structures. You're just going to kind of trust me here, all right? So again, what this thing is going to do, this molecule is going to do, is it's going to donate a pair of electrons to the ring. So this pair of electrons right here is going to reach down to that ring, all right? But it can't stop there because then carbon would have too many bonds. So this pair of electrons gets kicked up onto its neighbor, all right? Importantly, the arrows are maybe probably a little confusing. They're a little beyond the scope of this course. But what I'm going to show you are these resonance structures that are formed, and then we're going to take a look at those resonance structures. All right, so that pair of electrons comes down. That forms that new carbon-oxygen double bond. And that pair of electrons has jumped up onto that ring, or onto that carbon, forming a carbanion. My oxygen here has 3 bonds and 1 lone pair, so what is it missing?
Charge.
Charge, and which one?
Positive.
Positive. All right, so this pair of electrons got donated to this ring. So now we have this lone pair here, okay? Whoa. And this molecule is not very happy because it's got this lone pair on that carbon atom. But one of the things that stabilizes that lone pair are these different resonance structures that we can draw. So we're not just stuck here. We can also bounce this pair of electrons around. Oops. right, so that'll sort of have this bond and this lone pair change places. And it can keep going. All right, so I have these 3 different resonance structures that I can draw for that electron donating group. All right, and how did I know to get this? In this course, we don't talk much about resonance. I didn't talk to you about certain patterns that we can spy, that we know that when we see those, a molecule has resonance. For right now, you're just going to trust me, right? We have this electron donating group. When it donates that pair of electrons to the ring, we have these 3 different structures here, all right? And I'm going to get rid of these arrows that showed my electron movement so that we can focus on those structures themselves. Okay? Again, this negative charge is being stabilized by being passed around this ring here. But importantly, you'll see that it's not hitting every carbon around that ring. It kind of jumps to every other position. Not the pair position. Which position is being excluded relative to this group here? It's these 2. So excluding that meta position, absolutely. So what we see is that negative charge is being bounced around this ring, but specifically being bounced to either the ortho positions or that para position. Okay? Now, in these nucleophilic aromatic substitution reactions, we said benzene is the nucleophile. It's the electron-rich species. So this electron donating group that's adding even more electrons to the ring, is that going to make benzene a worse nucleophile or a better nucleophile? It's going to make it better because it's adding even more electrons, making it even more electron rich, all right? But it is specifically adding that electron density to only 3 carbons around that ring. So it makes this ring an even better nucleophile, but only in the ortho and para positions. Okay? So that means that if I started out with phenol and I did one of my electrophilic aromatic substitution reactions, it would direct incoming groups to those ortho and para positions. All right? So now we have our benzene ring is an even better nucleophile but only in those ortho and para positions. Okay, so again, if we take that phenol, right, that particular molecule had a special name, and we do one of our electrophilic aromatic substitution reactions. And it doesn't matter which one I pick. I'm going to randomly pick this one here because it's the first one that we discussed, but it doesn't even matter. Again, it's going to direct incoming substituents to the ortho-para positions, what we would call an ortho-para director. It made this ring better at being a nucleophile, but only in those positions here. So what we're going to get is a mixture of the ortho product and the para product. Importantly, no meta product is formed in this reaction.
wanted to show us, but we don't actually draw that in on the
You don't have to draw these in. This is just explaining why electron donators are ortho-para directors, because that negative charge is bounced on the ortho and para positions. But no, you don't have to draw. These resonance structures are explanation. They're not something that's required here. Okay? So the bottom line is we talked about how when we do if we do these reactions back to back, we could get these different products, and we got to know what's going to be formed here. What we see is that some groups that we put on the ring are what are called electron donating groups, and they're going to direct any incoming substituents specifically to the ortho and para positions. All right? And we'll pick up on this next time. We'll talk about electron withdrawing groups, which are meta-directors, all right? And then we'll look and we'll classify everything as either being ortho-para or meta-directing. Cool. And we'll pick up with that next time.